So I'm going to talk about Lithium, which is a split-brain resolver I started writing during my master's thesis at EPFL in a company I'm working at currently, Swissborg. So because it goes a bit into the details of Akka-Cluster, I want to start off the presentation a bit with explaining what Akka-Cluster is and just give you all the different things that we have to know for the rest of the presentation. So imagine you have a service that's running in that is like one single actor system, and after some time it's getting quite some requests, and you start maxing out the CPU, memory, and everything. One solution you have is to throw money at the problem in a sense and just buy bigger CPU, have it run like on a bigger computer, like bigger CPU, more memory and everything. But what you can also do is to maybe try to distribute your service. And that's what you can do with Akka-Cluster. So what Akka-Cluster does is kind of a way to have multiple actor systems connected together. So it's a way to have multiple actor systems connected together, and they can communicate over the network. So now you don't have your service running in on a single computer anymore, but you can kind of distribute it over multiple ones. So imagine, so in your original service, you had an actor that had to be instantiated once. So in a sense, a singleton. And if you think about it, having your singleton in an actor system is a bit more complicated than just being careful to instantiate it only once in your code. And so to be able to do that, Akka-Cluster needs to know what nodes are in the cluster, what their statuses are, and everything. So the different statuses nodes can be in are the ones here, so joining, up, leaving, down, and everything. There is always a leader. Well, most of the time there is a leader in the cluster that will take that state and move it. I'm sorry. So yeah, the leader will move the states of nodes to the next one and everything. And the way it does that is by listening to all the other nodes, and because all the nodes gossip what they think the membership, the cluster state is. So for instance, when a node joins the cluster, it arrives in the joining state. Then when every node has seen that, at some point they will have gossiped around that it has been seen in the joining state. When the leader sees that, it will move it to the up state and then gossip to the rest of the cluster, okay, this node has moved to the up state. But one issue you have is that when you start having an unreachable node, that means that there cannot be any convergence anymore. So let me explain first what unreachable here means. So for instance, in the case to handle singletons, the cluster has to know that a node, if like maybe a singleton is running in node 3 here, and when it becomes unreachable, we have to know if it's unreachable. So if we see if it's unreachable, that means maybe there's an issue and we have to start migrating that singleton somewhere else. So how do they figure that out? So very roughly, so here node 1 will ping node 3. So asking, hey, are you alive? Sending it ping. If it's alive, it will answer yes, or will ping back, and node 1 will say, okay, well, I tagged that one as reachable for now, and we're fine. However, what could have happened also is that node 3 has died. So it crashed completely and it won't answer the ping. But from the point of view of node 1, it's a bit more complicated than that. A bit more complicated than that. Because if you think about it, maybe node 3 is just very slow. So it might be GCing quite a lot and will just respond like take way too much time to respond to the ping. And so what we have here is actually that when a node becomes unreachable like this, so it doesn't answer the ping, there's no way to know if the node is actually dead or alive. The only thing we know is it doesn't answer anymore. And so this is why I said that convergence cannot be reached with unreachable nodes. So because let's imagine what happens if there's an unreachable node in the cluster and we'll just ignore it. So we say, okay, well, we'll just ignore the opinion of unreachable nodes here. Well, let's say, so what happens? So what could happen so is that then all the ones that are reachable at the moment will move to the next membership state, seeing a certain node as up now. But then when the unreachable one comes back, because it was just slow, we'll still see the cluster in the old state. And then you have, so your membership starts converging, and that's something that you really don't want, because every node in the cluster needs to have a compatible view of the cluster to be able to work correctly. So yes, and then a bigger issue that comes on top of this is that this means that if you have one node in your cluster that is just slow and becomes unreachable, one thing you want to do is maybe add more nodes to your cluster to kind of maybe handle the load more. But that's not possible anymore, because all the nodes will still be able to join, in a sense, to be in a joining state, but will never be moved to the up state. And only nodes that are in the up and leaving state are actually fully fledged members of the cluster. So joining nodes will never be able to take over the singleton, for instance, that was on the unreachable, that's on the unreachable node. So this is going to be our kind of example cluster for the rest of the presentation. So we have a 5-node cluster with a super important singleton here running it at 4. And then 3 sharded entities that we'll call Alice, Bob, and Charlie. You can imagine them maybe being, well, like 3 users of your cluster. So you have this cluster that's running in production, you're happy. And one day, at some point in time that you really don't want to hear about it, I don't know, in the middle of the night, some nodes become unreachable. So what we have is that from the point of view of nodes 1, 2, and 3, node 4 and 5 are unreachable. And from the point of view of node 4 and 5, node 1, 2, and 3 are unreachable. Both sides don't know if the other side is dead or alive. This might be just a network partition, or really they might have crashed. So again, you don't know what's happening. We only know we cannot communicate anymore with the nodes on the other side. So this is problematic, because, well, if you have a request that comes in from this side and it has to go through super important singleton, is not possible. You have your role, and same thing, well, if it means someone has to talk to Charlie or the other way around. So now your whole availability kind of goes down the drain until this is resolved. So I'm going to start off with what we shouldn't do here, because it's a good example to kind of understand. Yeah, I think that's a good way to go. So before we have this here, so again, this is the same one. And if you kind of dive into Akka-Cluster documentation, you figure out, okay, well, if a node is moved to the down state and it's unreachable, it will just be automatically removed by the leader. So, okay, we'll see. Well, let's do that. I mean, those unreachable nodes are problematic. I just want them gone. Let's see what happens. So let's do that. So we're starting first with the point of view of nodes 1, 2, and 3. So they will just remove node 4 and 5 from their cluster membership. And then from their point of view, they will look like this. So there's one cluster now, just with 2 nodes less, 1, 2, and 3. They'll migrate the singleton to themselves, start up the singleton, start up Charlie and everything. What happens on the other side, because actually they were still alive, there was just network partition, they will do the same. So they will down the nodes that are on the other side. And so you have to know that downing, you don't really down for the nodes on the other side. I mean, you can't talk with them. You just only change your state in the membership. So now, we have the other side, node 4 and 5, that do exactly the same thing. But what an exactly what happened in reality is just that both sides now created a cluster on their own. You have their single, so they don't have any nodes intersecting between them anymore. You have the singleton running twice now. You have twice Alice. So from here, so this is a split brain. So just one cluster that's split it in two different, completely independent clusters. So you can imagine this is really bad because, I mean, I don't know, if Alice is a bank account and you withdraw some money, so events come, so the request comes in from this side, you could technically double spend because this Alice has no way of knowing that, you know, the money is gone. So now what we should actually do. So what you should actually do, so I mean, this is the most automatic way, is use a split brain resolver. So it's kind of a misnomer in my opinion, because the split brain resolver doesn't resolve the split brain. So it doesn't let your cluster go into the state I was talking about before, but it will prevent it from happening in the first place. And so what it does is it will pick from all the partitions, it will make sure that that only one will survive and that all the other ones will actually down themselves, even if they're healthy, they will just kill themselves. So now Lithium. So Lithium is one of those split brain resolvers. It's an open source split brain resolver. It provides at the moment 4 different strategies, similar ones that the one are in the Lightband one, has support for multi-data centers. And up to a few days ago, I could say it will handle non-clean network partitions. So I'll explain later what it is, but I recently found a bug, so I have to solve that. That's why there's a little star there. So, why did I start a new one? And so what are the existing solutions? So the kind of de facto one is the one provided by Lightband. It has 5 different strategies, also multi-data center support. So it's kind of the most powerful one that exists at the moment. It's kind of fairly costly, but it comes with the whole subscription. So I mean, you get what you pay for. And so yeah, I can't say more about that one because I wasn't able to actually use it. So it kind of stops here. Then what I found on GitHub, so 4 different other one open source solutions. One I know is being used, actually the most simple one of them all, with the simplest implementation, is being used in production at Moya. I've heard that at Scala Days last year. And I found a blog post about another one that was used in production, I think 2 years ago, but I can't say. And then the two, so then there are 2 others that have quite a few different strategies, but as I'll show at the end of the presentation, they show some multi-node tests that I applied to them. Yes. So how do we start implementing a split brain resolver, and so how was Lithium implemented? So Akka provides a class that you have to extend called the downing provider. And that's the downing provider. And so you extend that class and you provided a props for your, kind of a way to instantiate your actor handling all of this. And then then you put the class name somewhere in your config and it automatically instantiates it. And so what this means is that Lithium is actually running, like, there's 1 instance per node. So it's not kind of a god thing flying above your cluster. So they're really independent little split brain resolver in each node of the cluster. And then very basically at the end of the world, Lithium will just give an award view. The word view is a enhanced cluster membership with a bit more metadata to be able to take a decision. So the decision could be, say, down yourself, down the other side, or anything. So, and all these, so finally, what we have to understand here is that they all do their work completely independently. So there are no messages exchanged between 2 instances of Lithium on each node, because you can't really rely on that, because there might be network partitions and there might be message losses and everything. So they all do their work on their own on each node. So this is very quickly the architecture of Lithium. Throughout the presentation, we'll understand a little bit better what this actually means. So there are three actors running: the reachability reporter, which in a sense listens to all the cluster information that's happening, and from that kind of builds up a better understanding of the reachability status of the cluster. Then there is a split brain reporter that will report on split brains, and the resolver that will finally actually do the real work and handles the split brain. So I'm going to start a bit with the strategies. I think it's nice to know which ones there exist, and then I'll dive a bit deeper into all the issues, actually, different issues that you could face when implementing split brain resolver. So I used the same naming as the lightband one because I couldn't find better names, and I think it just didn't make sense to kind of change the name just for the sake of name, not changing them. So we have keep majority, which is the strategy that will just pick the partition with a majority of nodes. So let's see how that works. So we have, again, our example from before. So here, node 1, 2, and 3, we'll see, okay, we're in majority because there are 5 nodes in the cluster. And so what will happen? They will decide to survive. And node 4 and 5 will decide to down themselves because they're not in a majority. So there are drawbacks here, because if there are too many partitions, for instance, there cannot be any majority. I mean, if you have a 5-node cluster, the majority is 3, and if you have partitions of 2, 2, and 1, no one will survive. So you can actually lose your whole cluster when that happens. Yeah. Next one is kind of a different variant of keep majority, static quorum. So this one, you have to configure. You will configure how many nodes there have to be at least in the partition for it to survive. So it will pick the partition that has at least n nodes. And this is useful if you have a fixed size cluster. Because if your cluster grows too large, this doesn't work anymore because n might not be a quorum. So again, this is the same idea. This side will survive, the other will down itself, and there we go. So in essence, it looks quite a lot like keep majority. Downsides, again, if there are less than n nodes, they will down themselves. If there are more, so if there are too many nodes for there to be, so that n is a quorum. So if there are more than 2n-1 nodes, meaning that there could be 2 quorums of n nodes, the cluster would just automatically let down itself for security. And same thing, if all the partitions are too small, the whole cluster will down itself. And it is interesting thing here is, so that it cannot lead to a split brain. I mean, keep majority is very flexible, but here we're a little bit less flexible because you have to have a fixed size cluster, but at least you have the security to know that this cannot theoretically lead to a split brain. And finally, the two last ones, they're kind of a different category of strategies. So keep oldest. Keep oldest, so we'll pick the partition with the oldest node. And what's interesting is that the oldest node is where Akka-Cluster actually runs your singleton. So if you have lots of singletons that you don't want to restart, to be restarted and removed from the cluster, this is an interesting strategy. So imagine here, so we have node 4, which is actually the oldest node because singleton S is running on it. So what will happen is that the bottom, so 4 and 5 will decide to survive, and 1, 2, 3 will decide them down themselves. So again, downsides is that if the oldest is alone, so if you have, I don't know, a 100 node cluster, and the oldest is just, there's network partition, and the oldest is just like living alone on the side, you will have 99 nodes that will be downed, So that's actually configurable, so you can choose if the oldest one is alone, if maybe you want to kill that one. And then finally, what's keep referee is what static quorum is to keep majority, and keep referee is is to keep orders, what static quorum is to keep majority, sorry. And this one will pick the partition with the referee node. So referee node is just in the configuration, you will just put the address of your node and we'll use that one. So here in configuration, we would have set node 5 as the referee. And so this side will decide to survive and the other side will decide to down themselves because they cannot reach the referee. Again, kind of the same thing as keep oldest. If the referee becomes unreachable, you have the same issue where you could just end up with a one node cluster, which is not what you want. And so if that's not what you want, you can still configure it to kind of, if it's alone, have that one survive. And again, like static quorum, this one cannot lead to a split brain. So you're a little bit less flexible, but at least this is very nice to have. So I have a little kind of decision tree to quickly help you choosing a strategy. Basically is if you have a homogeneous cluster, so no kind of nodes that are more important than the other ones, you can choose between static quorum and keep majority. And then if you have one node that's very critical, so for instance, if those are the singletons in a sense, so the oldest node, you could keep oldest. If it's one specific one, you could use keep for free. And there's a whole trick what you can do. So imagine you think, okay, well, my cluster size can just grow and shrink over time. And you only can use, so you think, okay, you can only use keep majority. But what you can do is to specify to Lithium a role to take into account. So what you could do is that if you have a subset of a fixed subset of your nodes that are do event sourcing, so you don't want to restart them, you can tag them with a role. Lithium will only take them in account, and then you can use static quorum, which can be useful. Okay, but now this is all fine. It looks very easy. I mean, you just check and just count and everything. But there are quite a few edge cases that that in all the other, at least open source ones, are not handling, and that actually can lead to split brains if you don't do it. So let's start with indirectly connected nodes. So before, what we always had were clean partitions. So nodes 1 and 2 would be completely cut off from node 3, 4, and 5, for instance. But what you could have is that just a single connection between two nodes. So here, 2 and 4 is broken for some reason. And so node 2 is actually indirectly connected to node 4 by going through node 1, for instance. So let's see what happens if we do this with the keep oldest strategy and the setting down the oldest if it's alone. So, so when node 2 will see node 4 as unreachable, it will start gossiping out to the rest of the cluster that node 4 is unreachable. And what will happen is actually that node 1 will receive that message and will actually believe it. So when you will look at nodes 1, all the nodes that node 1 can reach from what he thinks he can reach are node 1 himself, 3, and 5, but not node 4, because node 2 said it was unreachable, which is actually not the case. And the same thing, it will think it cannot reach node 2 because node 4 will have detected node 2 as unreachable and would have gossiped that to node 1. And so we have that exact same case here. So no one can see from here, all the reachable nodes for him are node 1, 3, and 5. For node 3 and node 5, it's exactly the same thing. Node 2 is a bit different because for him, himself is still reachable. So he will see node 1, 2, 3, 5 as reachable. And node 4 will see 1, 3, 4, 5. So 4 because he will not believe when somebody sensing, oh, you are unreachable. So now, okay, so this is how every node now sees the cluster. Let's see how this can go wrong. So 1, 3, and 5 will down themselves because, well, so node 1 will down itself because it cannot reach the oldest node, node 2. I mean, it's not here in the set of reachable nodes. So the same story again for node 3 and node 5. So they cannot, for them, they cannot reach the oldest node, so they will down themselves. And then finally, node 2 will say, okay, well, I can reach everyone. I'm the oldest one. Oh, well, and I'm not alone, so I down myself. And then finally, node 4 will see, okay, well, I can reach everyone, but node 2 is the oldest one. It's alone, so this means down oldest if alone, so it's alone. So node 4 will survive. And what we end up with now is with node 2 and node 4 still running and still running. And we have a split brain. So kind of a tiny split brain because we have a cluster of size 1 on this side and a cluster of size 1 also on this side. And so what Lithium does to kind of detect, because now we see indirectly connected nodes are problematic because you start having unreachability detections that are actually wrong, or in a sense that are wrong. So what Lithium does is it will look at the cluster membership, and if it sees that in the membership there is a node that has been seen as unreachable, and that node has seen at the same time that state, it means that it means that it's indirectly connected. Could imagine, so here what could happen is that, so node 2 detects node 4 as unreachable, will gossip it out, and then at some point, because all the nodes gossip between each other, node 4 will have seen that information, and the other ones will detect that. And so again, also node that's indirectly connected is also the observer by extension. So here, node 2 and node 4. And then what Lithium will do is just all indirectly connected nodes will just be down because will just be automatically be removed from the cluster because they can just lead to faulty decisions. Now, unstable cluster views. So a good thing to do is to wait for the view of the cluster to be stable. So you don't want to be to have the split brain resolver take a decision whenever the cluster membership is changing. So if you would do that, maybe it might change a second later and the whole decision might be different. The information might not have been gossiped throughout the entire cluster or partition. And so you could make a faulty decision. But this creates a problem. So imagine, so we have, again, the same network partition as before, but now nodes 4 and 5, for some reason, their view of the cluster keeps changing, it's unstable. So what will happen is that on the other side, their view is stable, it will converge very quickly, and they will, let's say this is keep majority, they will decide to survive. So from their point of view, well, they survive, and the other side has downed themselves. Then after a few seconds, actually some time configurable in down removal margin, Akka-Cluster will start up the singleton, so migrate the singleton. So, but actually what's happening on the other side is that they haven't downed themselves yet. It's still unstable. So they're still waiting for the cluster to become stable before being able to take a decision. And so what you end up with is for some time before they actually will down themselves, is that you now have 2 singletons running in the cluster here and kind of a transient split brain. And so this is a big problem which you could which happens quite a lot. So what Lithium does is that it knows it kind of can estimate when the other side will start up the singleton. And so it will detect when it takes too long to take a decision, and will just simply kill that petition. And so because at that point, so when we kill it, the reason why we kill it here, but even if that slow side would have survived technically if we waited long enough, because maybe it wasn't majority, we still kill it. We still kill it because since you don't have a good view of the cluster to take a decision on, you can't rely on it. Finally, and this is kind of a tricky one, is status changes during partitions. So this time, so we have this cluster with nearly all the nodes up, but nodes 2 and 3 just joined the cluster and are in the joining state. And we have here node 1 is the leader of the cluster. Then what happens is that exactly at the same time that the network partition happens, leader has seen convergence on those two nodes joining, and will start guessing out, okay, node 2 is now up and node 3 is now up. However, because there's a network partition that happens exactly at the same time, unfortunately, the other side, so this side, node 4 and 5, haven't seen that information yet. And so they actually still see nodes 2 and 3 as joining. And so what we have now is two sides of the cluster that don't see the nodes in the same state. So let's see what happens if now we just use keep majority without, just like that. So node 1, 2, and 3 will count, okay, we're 5 nodes in the cluster here, 5 up nodes in the cluster, we're in a majority, and I decide to survive. Then on the other side, node 4 and 5, so they see nodes 2 and 3 as joining. And we have to know that since nodes can always join the cluster, even during split brain, but not become fully fledged members in the upstate during network partition, they shouldn't be counted. So what will happen is that they will count, okay, well, we're 1, 2, 3 fully fledged members, and we're 2 here, so meaning we're majority, and we decide to survive. And so what you see here is that actually both sides decided to survive here. And again, so here you create a split brain. So the way Lithium fixes this, and I think Lightband also fixes this, is by just simply assuming that nodes that are joining on the other side are up. This is kind of a pessimistic view of it, because what could happen if, so this would fix the problem here, because node 4 and 5 would not be a majority, only node 1, 2, and 3 here, because now they all see the nodes as up, is that if they didn't move up on the other side, so imagine this that happened here, we would have both sides actually downing themselves and you would lose the cluster. But I think it's better to lose your cluster and having to restart it from scratch than to have a split brain and having to live with all the issues that arise from it. So now I think I can go again here, the architecture. And so the part I've been talking about the detection of indirectly connected nodes happens here in the reachability reporter that will just listen to all the membership events and reachability, and from that be able to infer which nodes are reachable, unreachable, but also indirectly connected. So there's a third status there. Then the split brain reporter, is the one that will wait until the cluster is stable, but also be able to detect when the cluster is unstable and we have to kill a partition because it's taking too much time to be resolved. And then finally, the split brain resolver here that will run the strategies I've been talking about at the beginning and do the actually kind of the dirty work of downing the nodes or downing itself. So I've been talking here, but actually what was the most work here is writing tests. It's so 70% actually of the whole project are tests. There are a whole bunch of unit and property-based tests. So what I was able to do is to extract the, to kind of simulate using property, like by generating different cluster views and applying them on the decision-making parts. And so I would generate a fake cluster, split it randomly in different ways and generating different kind of network partition scenarios and seeing how if every time there's only one partition that will decide to survive. And finally, so there are also, I wrote multi-node tests, which are kind of a pain to run because they take about 45 minutes, probably because it's quite inefficient. But that way you can really kind of run a cluster locally and really see nodes downing themselves or downing other sites automatically. And so these multi-node tests are actually not directly linked to Lithium per se. They kind of assume that, for instance, Kyiv majority resolves a scenario in a certain way, but I was able to apply them to all the other open source solutions. So there's not Lightband here because, as I said, didn't have the chance to be able to play with it. But we see, I can't remember exactly which one. So those are the two simplest ones that only implement static quorum. And so those are the two used in production and they actually pass the tests, which is, I think, quite safe to know, quite nice to know. And then the most complicated ones that fail all the tests, there's always something that fails, mostly because of the indirectly connected nodes, so the non-clean network partitions. Because they don't handle it, and here static quorum actually doesn't really care about indirectly connected nodes. This whole table has to be taken with a kind of a grain of salt, because as I said, it's the multi-node tests expect the split brains to be resolved in a certain way, like it's hard-coded which partitions should survive no split brain. Oh, okay, I forgot the conclusion slides, but yeah. So as a conclusion, when you start writing a split brain resolver like Lithium, it starts off pretty easy. I mean, you could, in a few hundred lines of code, just have the start, and I mean, you look at the cluster membership and all the reachabilities, and you make a decision. But what's most complicated, and what the other ones don't do, and what Lightband also does, is look at all those little kind of details. So the indirectly connected nodes, cluster when the state changes during during network partitions and everything. And that's actually where all the work goes, and which is hardest to resolve. I already have a few contributors with small things. Since yesterday, it now works with Akka-typed. There was a little one-liner that someone contributed. A new strategy is actually in the works, or at least someone wanted to work on it and is working on a PR on that, which is very nice. We have actually been using Lithium in production now since a few months. We have detected some issues, but it never actually led to a split brain. Just sometimes it just became a bit trigger happy. But we're resolving the issues one by one. That's it. That was it. So well, thank you very much.
One question, may I ask?
Yeah.
What are your future plans on Lithium features?
Yeah. So well, I mean, the one now highest priority is to fix the detection of indirectly connected nodes. wasn't a few days ago. But yeah, that another one's pretty interesting that a colleague of mine asked for is to publish events in Akka's event bus. So you could have actually some actor listening to them and actually publishing metrics. So you could have metrics so you could have metrics or alerts when Lithium starts doing things Other than that, like the fifth strategy, which is actually a strategy that that relies on something external. So like kind of like maybe having a database in which you kind of try to take a lock on one of the rows, and if you have the lock on the row, that partition will survive and the other one doesn't. So that's kind of the next strategy that someone is actually will be working on, hopefully. And yeah, that's it. What comes to mind?
A question that is about the testing. You said you use property-based testing, and then you also use the multi-node tests.
Yeah.
Are they combined? Do you use property-based testing in combination with multi-node testing?
So I mean, I don't. So what you mean is like if I use this at the same time, or?
Yeah, that your property-based testing generates scenarios that can be tested then with multi-node.
No, so what happens? So in multi-nodes, I just went through and hard-coded quite a few scenarios.
Okay.
And then the other ones actually only run, so they're kind of don't start up a whole cluster. So they fake those worldviews I was talking about at the beginning. So they create one and then just kind of splits it into multiple ones, like a network partition that would happen with all kinds of things happening, and then run them all those are kind of at the same time, and then just see if there's only one of them that decided to survive.
Yeah. Okay, thank you.
Have you considered a method that when an external system like an orchestrator, like Kubernetes, provides its view, the desired view of the world, and then this split plane resolver just adjusts the cluster to this external, like helicopter view?
Yeah, I've been thinking of that also a bit. Didn't go into it that much. This kind of what? I mean, the fifth strategy would be kind of that in a sense. At least you would be relying on Kubernetes or something, like you say, helicopter.
Like external health checks as well.
Yeah. So kind of thought about it in the back of my mind, but didn't put much more thought in that.
Yeah, the same sort as with Alexei, because we can have nodes of different weight, some TANs tolerations, and KHS have measure design about it. So nice topic to think about.
Approach that we can formally verify some parts of your algorithm. You say that you talking with the PFL folks which work. It's Leon or?
Yeah, exactly. It's the guys from Leon. Yeah. I'm not sure if they still use Leon. I think it's called Stainless now. They changed it, but I talked with one of the researchers there. I was in the class with. He came to meetup we had, so we talked about that. He thought it could be a good idea for some student project to try to kind of formalize the whole thing and do that. Like I said, I didn't have much contact with him anymore, and I think at the moment it's like with all the lockdown, it's it's kind of normal. But yeah, I think it would be a super great idea to do that, at least for some parts that I think are possible. I mean, you can't kind of model whole Akka Akka-Cluster and try to do with that. But like all the strategies maybe like on their own might be very nice to actually have like some proof that at least it works.
Yes, but I remember because proof is hard, but model checking is not so hard. No, it is hard computationally. But to write model checker, no, but model checking is not hard mentally because it is just program which enumerate all states.
Yeah.
We had a project when we check payment systems. And, yes, and it really works. And it works on 6 nodes. No, it's we maximum what it is dimension, yes, and we have 6 nodes. If we have 7 nodes, then we have combinatoric exploration. But 6 nodes we was able to calculate, and it was and it is work with 6 nodes. That with big probability it will work.
That's it's nice to know. Like it kind of makes it. Like now we're all relying on tests, so you kind of only you hope, you just try to hope to find bugs, but yeah.
Are you have external users for now? Or
I know 3 or 4 people / companies told me they were trying it out. I don't know how far they went with it. Yeah, so like that, I don't think anyone would be using it in production right now. I'm not sure I wouldn't do it either for now. I mean, we do it because I'm there, so I can kind of understand what's happening and quickly debug and quickly fix stuff. But yeah.
Can I ask you about your daily stack? What you use usually?
Yeah. So the daily stack. So because we're fancy, it's all like on top of Kubernetes, microservices and everything. Depending on which microservice we're talking about, some of them are just pure Akka. We use Akka, and then some other more kind of not smaller ones, but I think mostly the ones I work on are more pure FB. So there's some Akka HTTP, but like nicely wrapped in everything we're using. So we're kind of often using a mix between CATS and Akka, trying to mix it, and Doobie for databases and everything. Yeah, so we have 3 different Akka clusters. They're not big, so it's like, I think mostly they have 3 nodes. There's one with 10 nodes. That's a bit more heavy. So it's all events. Everything's like event. Most of Akka, where you have the Akka clusters and everything, it's all event sourced and it's all fancy stuff. Then the rest is just in your normal Postgres database, and
so you don't use Akka persistency, but you use
So we use Akka so I'm not on the team doing that, so it's a bit hard to say. I think we're on Akka persistence with based on Postgres behind, because we had bugs and we found bugs in the other library. I don't remember the name. I don't remember the name, but like the one that most people use, we found some bugs and we had issues. And then we So no, we use like the whole Akka, everything from top to bottom, also in some places, yeah.
And are you happy with the stack, or you want to change something?
No, I'm pretty happy with it. Yeah, actually, I'm pretty happy with it. Sometimes I would kind of love to kind of use Akka a bit less, which is hard. You know, it's kind of a framework. So when you're in it, you're completely in it, and that. But all in all, yeah, I'm pretty happy with the stack. I mean, like I said, we're using CATS and Doobie and all the nice libraries. So at least we have a few nice like nice things to play with, like if you like pure FP. Yeah, no, I'm pretty happy with the stack. Yeah.
Yes, but I am not sure I understand how you merge actors and cats, because if we have, for example, a future from or something from actor, yes, then they will return. Then all what they can do, then send us messages, yes, because they can't touch actor state. So how you when we look at this, we think that actor is one word and future and task is other word, and this word not work well each.
No, that's true. So you kind of, I mean, the way I see it is like they talk in PRP about the end of the world. So the main where you run everything, and that main is just like in every receive of your actor. So I mean, there's still message passing and everything, but then maybe the computations we do inside the actor, we kind of build them up outside with maybe some IO, well, sync IO actually, because you have to run on one thread, but doing that for actors. And then, I mean, then if you talk about Akka HTTP and Akka stream, you can kind of wrap them nicely in some way and everything. So we have you have Akka stream, and one of the stages is to compute something. So that is just some IO, then we transform to a future, because we just to build stuff. You build stuff up on the side, and then you throw them at Akka, and that one goes like .run, and so it's still inside Akka. Is still kind of the Akka actors is really the outside of it, and we're just still staying inside. So. It's not. We didn't solve the whole thing yet.
Okay, and do you use a classical actors or typed?
We are still classic for now. We didn't migrate to typed. We tried at some point, but it was like actually a year back or so, and there were still things missing. I think there was a whole issue with Akka persistent typed also. So we're still at Akka just untyped for now, and it works.
Okay, and you work with what is interesting that you work mainly with Scala, but are you follow any other development in programming languages?
No, I should. At some point I followed Rust a bit. Just because when I used Rust, it had the same feeling as the first time using Scala. It just like felt something very nice, and I was pretty impressed by the error messages and everything. But I, with all my work and studies I had before, you kind of stopped really following other languages. I mean, I keep an eye out on what's happening, and I don't know, just looking at reading some articles about Go to kind of understand what they're about and everything. So, but I'm kind of more kind of a Scala fanboy, so kind of stuck in that stuff. I should actually, I should maybe open my eyes a bit more to the rest. That's true.
But Rust system is interesting. I wonder, it's already talked about Rust, but it's system language. It's really too hard to write something because it's slow. It's slow to write because you need to think about memory management. So experience from my friends, I personally not use Rust, but I have friends which use Rust, and they say that all great, but you need to think about borrowing. It takes time.
It's a completely different kind of mindset you have to take. But at least error message is very nice. So it's like, no, you can't because this one has now the ownership, so you can't do this, and it's pretty interesting. But it's a different mindset. But I think it's kind of the same kind of mindset change you would have if like when you start Scala with all the type, you know, with the type system, and you're like fighting the type system and this kind of thing.
Returning to when we should choose the Akka and when we should choose a Kafka.
I'm not 100% sure to understand, but maybe, I mean, I'm going to tell something and maybe answer something and you tell me if I'm wrong. So first at work, I mean, like all the different services are Akka. I mean, there's no kind of Kafka, no, really Kafka inside per se. I mean, all the services, they kind of talk together via Kafka topics. Internally, you have Kafka topics also to kind of go from like command and then events and everything. When I think they're kind of two completely different things, Akka and Kafka. I mean, in a sense.
Are you wrote? I understood. Are you wrote own processes? Own Kafka
consumers?
No, not consumers, but processes. Processes. Live inside Kafka.
Yeah.
So
no. Okay. So for me, I mean Kafka, you consume or you produce into Kafka. But then.
So yes. So I understand your mindset. No, it's what I was asking because it is possible to write something which will work inside Kafka.
Okay.
Yes, and it's compatible with Akka usually.
Okay, I didn't know that. Okay, no, sorry.
Right.
No.
Well, I don't have questions. I really just have to try the system out first, and then I'll have questions.
Oh yeah, probably.
But as far as I understand, it's fully dynamic, right? It makes decisions and reconfigures on the fly.
Yeah. I mean, it just like it listens to everything, the events inside the Akka, you know, understanding what who is part of the cluster and who's not, and what they're, you know, if they're seen as unreachable, and then from that kind of builds up a state that dynamically changes, and then when something happens and has to be done, it just goes this way and just starts killing nodes, and then so it does that. Or it's all. I mean, there's nothing to do. I mean, the configuration is static, that you shouldn't change while your cluster is running. I mean, most of the time, it's kind of dangerous to do it. We do it sometimes where you change one little configuration and you just like redeploy your, like you don't redeploy a cluster, like you don't node by node, you do, and you just hope it goes well. But yeah, no, configuration is still static. I mean, we define it at the beginning. Yeah.
But if you add the node, you should restart each node.
Yeah, so when the node is down, it should be restarted. So that's kind of like in this case, is Kubernetes that will restart it because it sees, oh, there are not enough like replicas, and we'll start one up. Actually, one thing maybe I can talk about. So it's if you use Kubernetes with any split brain resolver, you have to be kind of careful with because what can happen is that so Kubernetes will happily restart your node, but if it's still if it's complete network partition and it starts up on the other side and it sees no other members, it will actually create a cluster on its own. So what you should do is actually, from when you deploy the first time you deploy your cluster and it's completely up, after that you should deactivate the option in Akka-Cluster that the cluster can actually, a new cluster bank can be created. So we have kind of a step where it deactivates Lithium and it activates cluster creation. You deploy your cluster, then you dynamically, when that's done, you dynamically change the configuration and you say, okay, now Akka-Cluster, I don't remember the name of the configuration exactly, but it says like, if you can create a new cluster from scratch, you deactivate that and then do a rolling update. And then so what happens is that at least if nodes are downed and they restart, they will always try to rejoin the existing members and not create a cluster on its own. Because what could happen is that actually Lithium doesn't make any error, but it's actually Kubernetes that will kind of create a second cluster and
cluster is the same size.
So that's so this is something you have to be very careful about, that one. Yeah, it kind of, we had a problem with that because we didn't know about that and we had to
Okay, so thanks.
Yeah, thanks for all the questions. Bye bye.